So here's our latest installment, exponential growth and decay. It's all about applications of the exponential functions that we've been talking about. Now, those exponential functions are all those things that were y equals a times b to the x. It was all completely based on repeated multiplication, where b was the number we were multiplying over and over and over based on how many times x told us to do it. So more specifically, exponential growth. We can use this for things like simple interest, which is really kind of like inflation, bacteria growth, population growth, and then there's also compound interest, but that takes a little tweak to the formula we can use for everything else. So for those first three items, our simple interest, our bacteria growth, our population growth, the generic format for that is y equals a times b to the x, where a is a positive number and b is bigger than 1. Now, that's all well and good, but it's not super helpful when it comes time to actually apply it to some of the problems that we'll encounter. So we want to have a better version of that formula. So more functionally, it's y equals a times the quantity, 1 plus r, to the t power. Now that 1 plus r, we'll just make that a little clearer. That is a 1 plus r. That's how we get that b greater than 1 idea. A, that's the initial amount. That's how much we have when we start. Sometimes it's the amount we deposit. Sometimes it's the amount of cells that are in a petri dish. It's the number of people in a given year before we start calculating. But it's the initial quantity of something. Our growth factor, that's really the b value. 1 plus r is b. 1 plus r so that we can be greater than 1. R is specifically the growth rate. Now we write that as a decimal. So 1 plus 0.07 if we grow by 7%, which 1.07 would be our growth factor. And then t is time, usually measured in years because that's usually the period of time we're given for our rate. So just to recap, a is our initial amount, b is our growth factor, r is the growth rate, and t is time. That other formula that I was talking about, the situations where that simple formula isn't really going to apply. Well, it's a equals p times the quantity 1 plus r over n to the nt power. Subtle adjustments because compound interest is about the fact that many times the way that banks operate is they tell you they compound things quarterly, which means the interest rate they tell you is an annual rate. It's the amount of interest they give you every year, but they don't actually calculate it every year. They calculate it more frequently than that. So there's got to be adjustments to the formula to account for the fact that it's not a one and done kind of a situation. So A, that's our account balance, right? That's how much money is in the account for whatever period of time we're calculating. P is our principal. That's the initial deposit. It's how much is in the account before we calculate. R is still the rate. In this case, it's going to be an interest rate. The N is the newcomer to the equation. N is the number of times that we're actually going to calculate. If it's quarterly, we're going to calculate 4 times a year. If it's monthly, we're going to calculate 12 times a year. If it were weekly, we'd calculate 52 times a year. And that shows up twice in the equation. And then T is still our time period. The time period for T needs to match the time period for our interest rate. So if our interest rate is given as a monthly interest rate, our time period needs to be monthly. If our interest rate is given as an annual interest rate, our time period would be years. Moving on to growth, moving on to decay. Exponential decay, things like depreciation. They tell you that your car loses value the second you drive it off the lot. That's loss of value is depreciation. Radioactive decay, half-life of things, carbon dating, that all falls into this category. So our generic model for that is y equals a times b to the x, that exponential function formula we've seen before, where a is greater than 0, and 0 is less than b, which is less than 1. So b is between 0 and 1. It's going to be a fractional value. It's going to be a decimal. So we can get a more functional representation of this as well. Notice that the only change that's been made from the growth formula is that now instead of 1 plus r, we see 1 minus r. Most of these values don't change in terms of how we talk about them. A is still going to be that initial amount. Our decay factor is that whole thing. That's our b value. 1 minus r is b. 1 minus r, which if r is a rate written as a decimal, right, our decay rate, 1 minus r will give us some value between 0 and 1, which is what exponential decay specifically calls for. And then we've got our time period, t. These are the formulas that we need to use for the applications that we're going to look at. Make sure that we have them in our notes. Make sure that we've taken a little time to look them over and understand what each piece is worth, and we'll cover the actual application of them to some problems in class.